Digital Theodolite. It is a measuring tool, designed to work with angles both horizontal and vertical. This instrument is more precise and accurate than a magnetic compass. It ensures that angles make a safe and accurate structure. It has an accuracy advantage by utilizing averaging of repeating angles. It automatically reads the angles, and discards possibilities of human errors. It is more compact and light. The instrument is combined with an electronic distance measurement instrument, which automatically records angle and slope distance from just one setup. The table shows the difference between digital theodolite and dumpy level. Digital theodolite consists of targeting sight, objective lens, LCD display, operating keys, circular vial, tripod base plate, handle, handle screw, center mark and vertical plate, horizontal clamp, tabular vial, focusing ring, optical plummet, communication port, leveling screw, battery case, eyepiece, telescopic fin motion, telescopic lamp, tri-arch. Let's start setting up the instrument. The whole procedure is done in 3 steps: centering, leveling and focusing. Let's see centering first. It is the process of setting of the instrument exactly over a station. It can be achieved by following steps. Place the instrument onto the tripod head. Turn foot screw of tri-arch into its position. Now switch on laser plummet. The electronic level appears in the display. Next, position tripod legs, so that the laser beam is aimed to the ground. Finally, turn the foot screws of the tri-arch to center the laser beam exactly over the ground point. Move the tripod legs to center. The circular level is fixed. Second is leveling. Before starting the leveling, all the foot screws are brought to the center of their run. Now follow steps. Plate bubble is placed parallel to any pair of foot screws. Now turn the bubble plate through 90 degrees. Turning the third foot screw either clockwise or anti-clockwise, the bubble is brought to the center. Rotated through 360 degrees about its vertical axis. If the bubble still remains in the center position. Final step is focusing. Eyepiece is focused so that the crosshairs can be seen clearly. To do this, the telescope is directed. A piece of white paper is held in front of the object glass, and the eyepiece is moved in or out by turning screw in clockwise or anti-clockwise until the crosshairs appear clearly. The whole operation is conducted very carefully, but sometimes errors occurs. The sources of errors could be instrumental errors that are non-adjustment of plate bubble, line of collimation not being perpendicular to horizontal axis, horizontal axis not being perpendicular to vertical axis, line of collimation not being parallel to axis of telescope, eccentricity of inner and outer axes, graduation not being uniform, verniers being eccentric. Personal errors that are: the centering may not be done perfectly, due to carelessness. If the clamp screws are not properly fixed, the instrument may slip. The focusing in order to avoid parallax may not be perfectly done. The object of ranging rod may not be bisected accurately. Error would also result if the verniers are not read because of oversight. Natural errors are: high temperature causes error due to irregular refraction. High winds cause vibration in the instrument, and this may lead to wrong readings on vernier.